So this is outside the context of this course, but you notice that I am typically running these notebooks on a server, not on my machine. Second, I don't have to log in. So many times when you have to log into a server, when you have to use a notebook over the server, you have to typically log into the server. But I don't do that. Does anyone know why? I don't need to. Sorry? So I'm using a passwordless SSH, which is something of convenience if you want to use. Coming back to today's class. So I hope all of you have gone through the video recordings that I had shared over the previous 2-3 days. The first one was what topic? Does anyone remember? Sorry? Geometric interpretation of linear regression. The second one was multicollinearity and dummy variables. So today we'll talk about gradient descent, which I think should make you happy because all of you want to just learn neural networks. And gradient descent is something which gets you towards neural networks. It's an optimization technique. Previously, we have seen these two plots. These are known as the surface plots and the contour plots. So without looking at, assuming you didn't have a look at the screen, can you make the contour plot for z equal to x square plus y square in your notebook? Z equal to x square plus y square in your notebook, the contour plot. The important thing to remember about contour plots is you have to plot the locus of z equal to a constant. So firstly draw x square plus y square equal to 1. How does that look like? Then x square plus y square equal to 2, so on and so forth. If you do that, you get your contour plot. Next lecture I have to close the door at 8:35 because I think many of you are not taking it seriously. Okay, has everyone been able to draw the contour plot? Does it look like what you see on the following slide? So again, importantly, we need to know the relationship between the surface plot and the contour plot. The surface plot in this case is a 3D surface that you have made. So z as a function of x and y. Whenever x and y are large numbers, z is a large number. When does z take the minimum value? At x equal to y equal to 0, right? And at that, the value of z is 0. So therefore, you can see that it is this bowl-like shape which the surface has. Now, contour plot is, think of a bowl-like shape and you are cutting through it. You are making some cuts through it in the xy plane, right? So at z equal to 1, at z equal to 2, at z equal to 3, so on and so forth. And therefore, you get varying circles. You get circles of different radius. The inner circles are z equal to, let's say, 1, 2, 3, 4. So quick question. If you go from z equal to 1 to z equal to 2, there is an increase in the radius. Right? Versus if you go from z equal to 4 to z equal to 5, there is again an increase in the radius. In which case is the increase in the radius more? When you go from z equal to 1 to 2, there is an increase in radius, and we go from 4 to 5, there is an increase in the radius of the circles. Which of them shows a greater increase? The first one? Right. So this also helps us to understand the gradient, the concept of gradient which we have earlier done. So given this function z, which is a function of x and y, if you put in scalar values of x and y, what is the value of z that you get? It is a scalar or is it a vector? It's also a scalar, right? Now we have looked at the definition of the gradient. How would you define the gradient of z with respect, how would you define the gradient of z with respect to the inputs? So remember, the gradient that you're computing is you're finding out the partial derivatives of the function with respect to the individual components of the function. The individual components of the function are x and y. So, therefore, we can compute the gradient of this function f of x comma y, typically denoted by this symbol, is equal to the partial derivative with respect to the first component and the partial derivative with respect to the second component, which if you calculate will come out to be 2x and 2y vector, right. So, the gradient is a vector of the length of, what is the length of the gradient vector? In this case, it is 2 in general, the number of the input variables into the function. Right. So, I have written this statement here. Gradient denotes the direction of the steepest ascent or the direction in which there is a maximum increase in the function. Right. Can anyone explain what you understand by this, and if that relates to anything that I have drawn with respect to the arrows in this diagram? The gradient denotes the increase, the direction of the steepest increase in the function. Sorry? The longest of the arrows. Okay. So, so now go back to the surface plots that you have, the surface and the contour plots that you have drawn. Right. Let's pick up a point x equal to 1, y equal to 0. So, just mark it in your notebook, x equal to 1, y equal to 0. So, here it would be something like this, x equal to 1, y equal to 0, right. Now, if you want to increase z at the quickest rate, you can go in different directions. In which direction should you be going? Should you be going in the y direction, or should you be going in the x direction, or should you be going in the minus x direction? Right. So, if you go in the, let's work this out by some example if you want to. So, if you have x equal to 1, y equal to 0, if you go in this direction, you can see that the radius, the circle will become, the circle will take on a bigger radius as quick as possible. So, therefore, that is the direction of the gradient. Importantly, this tells you that the gradient you are defining, you are calculating at a specific point, right. At x equal to 1, comma 0, you can see that the gradient vector, if you put here, it will come out to be 2, comma 0. So, it indicates that the maximum increase in the function occurs in this direction, in the x direction, and 2 is the length of the vector along the x direction, 0 is the length of the vector along the y direction. But if you were to pick up a different point, let us say x equal to 0 and y equal to 2. So, x equal to 0, y equal to 2, you can see that the direction of the gradient would be now different. Now, the quickest way to go would be in the direction of the y axis, right. So, thus we can define the gradient in this way. In programming frameworks like Torch, JAX and TensorFlow, etc., there are very nice procedures in which you can automatically compute the gradient. Earlier on, this was very difficult when we did not have automatic gradient computation capabilities. Let us look at some simple code for this. I will be showing two different ways in which you could have computed the gradient. One is a functional way. So, I have defined this function f as a lambda function x comma y, which is x square plus y square. So, those who do not know about lambda functions, this is equivalent of writing def of f of x comma y and return x square plus y square. This is just a quicker way to write this. So, these are known as lambda functions in Python. Now, f takes two inputs. So, if I find the gradient with respect to the function f, and I will have to evaluate it at another set of inputs, right. The important thing in this particular implementation which I am showing you is, you given a function as an input and you get another function as the gradients, as the gradient. So, you learn you have a function and you can learn a function which is the gradient of the original function. We do it this way. So, I am calling torch.functional.gradient. I pass in the original function with respect to which I want to find out the gradient. I give the argument numbers. So I want to give with respect to the 0th argument and the first argument, I want to compute the gradient. And f dash, if we now look at f dash, it's a function, right? It's a function which takes two arguments, x and y, right? So in this way, I'm showing you that you start with a function, you call torch.func.grad on it, pass in the respective set of argument numbers, you get another function. And now this function, if I want to compute the gradient of this function f at values 1, 1, so I use this function f dash, which is the gradient function. I pass in the value 1, 1 and I get my answer 2, 2, which is as you'd expected because the gradient you'd calculate was the vector 2x and 2y. Although in this case I am looking at I'm passing in scalar arguments. I could have also done in a vectorial way. How would you do that? So here I'm passing in two scalar arguments. Could I have passed an array of size 2? Would that have still worked? So what I'm saying is, let's say f2 let me just create it this way. And let's say this is some argument. I could have created x, y equal to argument and return x square plus y square. Let's assume this is our function. Now, if I do torch.func.grad of f2, the default argument is always the 0th argument. So I get another function which accepts a single input at this time. So if I pass in torch.sensor of 0.0, 1.0, I get 2, 2, right? Which is the same answer. So I've shown you two different ways in which you could have solved this. Typically in machine learning, we will be using something like this. In fact, in this case, we are doing the argument unpacking. We will not even do that in many cases. We will directly use the vector notation for doing things. But I just wanted to show that you could have done it this way also. And the more popular way, which you will see in many PyTorch tutorials, is to call something known as the dot backward method. So I define two tensors. I say that we require the gradient with respect to these quantities. So I mentioned the torch, I give the value, give the required grad equal to true, compute z equal to the function of x, y, z dot backward, and x dot grad, y dot grad if I compute, it gives me the same set of values, 2, 2. Again, I could have done this, I could have used f2 instead of f. So these are some permutations, combinations you can check. So this is a good exercise to confirm our understanding of the gradients, highly recommended. Any questions in this? Z dot backward. What is the use of z dot backward? So z dot backward starts off something known as the back propagation, which we'll study when we study AutoGrad and neural networks, which will ensure that we are able to compute the gradients with respect to the original quantities. So if you were to before backward, if we print out the values, and if we print out after backward, before the backward pass has been initiated, there is no value in the gradients because you don't know with respect to what you're computing the gradient. Once you have created a function, which is function of the inputs x and y, then you call the backward method on it, you are able to propagate the gradients or compute the gradients. We'll study this in more detail. This is enough for you to now start with your assignments, where one of the question would be to use gradient descent for linear regression like problems. So you can pretty much use either of the two variants. The first one is known as the functional approach, which is transforming functions. You start with a function, you find the gradient of the function. The second is to use the dot backward method. In both of them, you will get the same answers, just two different ways of computing. The first one is also very commonly used in JAX-like frameworks, which is a functional way. Okay, so once we have seen the gradients, we will be now using the gradients in some kind of problems known as optimization problems. How many of you solve optimization problems or have solved optimization problems? I think all of us solve optimization problems, but we just don't think of it. So can anyone tell me any optimization problem they have solved today? So let's say your goal is to maximize your learning in a lecture while minimizing or while set of certain constraints. One of the constraints is that you should not be missing your breakfast. The other constraint is that you should not be missing out on certain sports, you should not be missing out on your daily sleep quota, etc. Right? So you are trying to solve a maximization quantity with respect to certain constraints. So when you have these certain constraints, you are solving something known as a constraint optimization problem. There are certain kinds of constraints, linear constraints, non-linear constraints, equality constraints, inequality constraints, which are a lot of problems which you study in the branches of optimization. For our cases, we will be looking at some very specific kinds of optimization problems. For today, we will be looking at, so we have already also looked at, in the case of linear regression, we had an optimization problem. We wanted to minimize this function, which is y minus x theta transpose y minus x theta. If you remember, this is the same as epsilon transpose epsilon, which is the same as summation epsilon I squared, which is the same as sum of squares of the residuals that you are getting. All of these are equivalent quantities. We said that we want that number to be a small number. So here, what do you think is y minus x theta transpose y minus x theta? Is it a scalar, vector, matrix, tensor? What is it? Scalar, right? It comes out to be scalar. What is theta? Scalar, tensor, vector. It's a vector, typically some d-dimensional vector. If your input data is d-dimensional, then your theta vector is d-dimensional, d plus 1 dimensional. D plus 1 dimensional to also accommodate for theta naught term. Input data d-dimensional, theta vector d plus 1 dimensional. So we had previously solved this problem f theta equal to y minus x theta transpose y minus x theta using elementary calculus, multivariate calculus. So we had found the derivative with respect to this quantity, set it to 0 and computed the normal equation, which was theta hat equal to, anyone? X transpose x inverse times x transpose y. But there are certain issues with that, which we'll uncover in today's lecture. I don't know if you've already thought about them or not. So we'll be focusing just on the maximization or minimization of functions with respect to no constraints today, which is also known as unconstrained optimization. So for example, in this method, f theta equal to y minus x theta transpose y minus x theta, this is currently unconstrained, you have to minimize this. What could be some set of constraints that you could put in this optimization problem? Theta, okay, theta not 0, so that's not a specific number kind of a constraint. What else could you put? Theta. Theta is a unit vector. We sometimes have such kinds of constraints. So theta as a unit vector means what? Can you mathematically put that? Theta transpose theta is? Or you could say theta transpose, we could talk in terms of theta transpose theta, or you could talk in terms of the norm of theta vector. Right? Certain cases you want to put some kinds of constraints like this, or theta transpose theta is less than a quantity, is greater than a quantity, theta is, the norm of the theta vector is less than a certain quantity. All of these are some constraints which we will study when we look at regularized linear regression. But for today, we will be solving this kind of a problem. We want to find out that optimum theta which minimizes some function of the theta. And for this, we will be using something known as gradient descent. So we have already looked at the gradient, right? The gradient is what? Can anyone again remind us? It is a vector corresponding to the direction in which a function increases at the quickest rate. And now we have something known as gradient descent. So descent typically means going down. So if this should give you an idea that we are looking at changing the value of a function, changing the parameters of a function in a way that reduces the value of the function the quickest. So we typically use it to find the minimum of some functions in unconstrained settings. Very important specific of this algorithm that it is an iterative algorithm. So before this, have you looked at any other iterative algorithm? How do you find the roots of a polynomial? Using what method? Newton-Raphson methods. Is that an iterative method? Is that a direct method? It's an iterative method. By iterative method, we mean that we start with some values and we iterate over those values. In this case, we say that we improve our estimates over time. And the other details are it's a first order optimization algorithm. What do you understand by first order method? Good. So whenever we hear terms like first order, the default answer which should be in our head is somehow related to Taylor series, because that's where we also look at various order approximations. And it is also known as a local search algorithm or a greedy algorithm. Where else have we looked at a greedy algorithm? Decision tree. What was the greediness there? We choose an attribute based on which gives us the maximum information gain at that level. So the greediness is we just want to compute a good tree at that level. We don't look at the future. So similarly, here it's also a greedy search, local search algorithm. We'll see how that's the case. And this is the main algorithm in just one slide. So we initialize, it's an iterative algorithm. Iterative algorithm means that you start with certain value and then you iterate over it. So let's say we want to minimize a function f of theta. We start with some initial value of theta. In our cases, theta would generally be a vector. So you initialize theta to some vector. You find out the cost function or some function which you want to optimize, the objective function f of theta. You find out the gradient of the cost function at the value theta. Right. So f takes in a vector, gives a, what kind of a function is f? It takes in a vector, it gives you a scalar, right? So therefore, if you compute the gradient of f with respect to theta, what do you get? You get a vector of the size of length of theta. And if you give in the arguments of theta, you'll get again some value. And this is the main update rule for different number of iterations, because it's an iterative algorithm. We say that our updated value of theta is the older value of theta minus alpha times the gradient computed at the older value of theta. There are quite a few terms going here. Let's go over this again. Our current value of theta is theta at I minus 1th iteration. Our gradient is the delta f function, right? It's a function of the length of, or it's a delta f we can think of as a function. Now we given these values, so we can compute the gradient at that specific function. So, and this will turn out to be of what size? The size of theta. Again, think in terms of simple calculus sizes, right? So if this is size theta, this is size theta, this also has to be size theta, and which we have verified also. The gradient is size theta. So this is the main rule. Now we'll go on slowly towards deriving this rule and seeing how to use this in practice. Any questions till now? Okay, we come to Taylor's series. So can everyone just take a minute and try to write down Taylor's series expansion around a point x naught. Some of you may remember, may not remember, we'll go over it, but let's see if you remember it or not. Taylor series expansion of a function f of x around the point x naught. The no laptop policy also accounts for no iPad on tablets. So don't look it up on your devices. If you know, you know. Otherwise, anyway, I'll share. So before we go into the details, let's recap Taylor's series in a very broad perspective. We have certain functions which we want to approximate with what kind of functions? Sorry? Can be louder? With polynomials. So we have certain functions which could be any generic function. You want to approximate it with certain polynomials. Why do we want to do that? Why do we want interpolation? So when do we try to approximate things? When the original thing is hard to compute, we don't know much about it, etc. Right? And you can do it for interpolation also. Right? So 3 Blue 1 Brown channel on YouTube has an excellent video on this. I highly recommend you to go through it. So and if you also remember in physics, and that's the example I think 3 Blue 1 Brown example also says. In physics, when theta is small, what do we typically approximate sine theta with? Theta. Why do we do that? Taylor's, one of the consequences of Taylor's series. Right? So now theta is much easier to use in various calculations, etc. Right? So therefore, polynomials make our life simpler, and thus we will be using it for various kinds of applications. So it's a complicated slide. Let's go over it step by step. So we've said that we want to approximate a function f of x, but the important thing is to not just approximate it everywhere. We generally want to learn some local approximations. If we talk about local approximation, it means that we have to give certain point at which we are approximating. So we say that we want to approximate function f(x) with polynomials around a point x naught. Right? So we'd expect the approximation to be good around x naught, but maybe not good everywhere else. And the polynomial is given as, so the polynomial approximation of the function f(x) is the function evaluated at x naught plus the gradient, the derivative y1 factorial into x minus x naught, and the derivative you evaluate at the point x naught plus the double derivative evaluated at x naught into x minus x naught the whole squared by 2 factorial, etc. Right. So this is showing the degree 0 term, degree 1 term, degree 2 term, so on and so forth. Now this is when we are dealing with scalars. We have a same formula, but in the multivariate case. So there we will be dealing with vectors. X becomes a vector. So if you want to approximate a vector function, we do pretty much the same as before, just that we'll have to take care of the shapes and sizes, and we'll have to use things like transposes to keep track of shapes and sizes, as well as instead of just the derivatives, we'll be looking at the gradients, and this is the gradient del f. What is this expression, this term called? It's called the Hessian. Right? So if our original function takes n dimensional input, what is the size of the gradient, dimension of the gradient? N cross 1. What is the dimension of the Hessian? N cross n. So we'll see the Hessian if we go on and study second order methods, but for now we'll just be looking at the first order term, which is just the gradient vector. Okay. Using this formula, can you write down the approximation for the function f(x) equal to cos of x at x naught equal to 0 up to some degree terms? Can you write that? The approximation of f(x) equal to cos of x around x naught equal to 0.0. Okay, do we have the answer? Approximation of cos x using polynomials from the Taylor series is at x equal to x not equal to 0 is 1 plus something, 1 plus 0. So, if f x equal to cos x, we want to evaluate at x not equal to 0, f of x naught we first calculate, which is cos of 0, which is 1. F dash of x, you first find out the derivative with respect to the function. So, derivative of cos is minus sign, you put the value 0, you get 0. Double derivative is minus cos, you put 0 as the input, you get minus 1, and you put in the remaining terms. So, if we had to write a second order approximation or second order Taylor series for this, we would write f x equal to 1 plus 0, which is f dash x, into x minus 0 plus 1 over plus minus 1 over 2 factorial x minus 0 whole square, which is 1 minus x square over 2. So, this is the approximation which we can learn. Will we have odd degree terms in this expression? No. Why? Because you will alternatively get cosines and sines at 0 will always give you 0. Similarly, if you were to try to approximate the function f x equal to sin x at x not equal to 0, what order terms will you get? Odd terms. So, x minus x cube over 3 and so on and so forth, 3 factorial and so on and so forth. So, thus you can see that if you had forgotten how sin x equal to is approximated as x, if you just put in Taylor's series and you look at the first order approximation, you get sin x approximately as x for small values of x, which is again to say that this approximation that we are getting is very local in nature, which means it only holds around the specific value of x naught. Now, let us look at some code to generate this. So, if we have a function, I am again using a lambda function, a cosine of x. I plot the function's value from minus 2 pi to 2 pi, and this is what you get, you would expect. We are trying to approximate the function at this value, right. So, if we go back to the slides, if we just consider the first term, what is our approximation? F x equal to 1. Is it a bad approximation? If we only look at x naught equal to 0 in the very immediate vicinity of it, it is an okayish prediction, it is an okayish assumption, approximation. So, I have written this sophisticated looking code. This takes a bit of time to write it correctly because you are dealing with some I and I minus 1, but the important thing is that I am again using torch func.grad. So, I am calling this within a loop so that I can successively compute f dash, f double dash, f triple dash, so on and so forth. You can look at this code in detail, but I can first just show you a simplifying view of this. Right. So, if I look at the nth order approximation of the function f, which is cosine of x, I am looking at the order 2 around the point 0.0, and then the approximation that I get, I also plug in a value of x so that I can look at the polynomials function that I have learnt. So, importantly, while I am doing this, I calculate f of x naught, I calculate f dash of x naught, I calculate f double dash of x naught. These things are happening here inside the loop, and then I am showing you the learnt approximation, which is f x equal to f of x naught plus this quantity is 0. So, x minus 0 raised to power 1 by 1 factorial plus this quantity is minus 1 into x minus 0 square divided by 2 factorial and so on and so forth. Right. So, the expression is in this fashion. Let me okay. So, now what I have plotted is the second order approximation of cosine of x using this polynomial, which is the orange polynomial. And can you notice that it's a fairly good approximation, at least in the vicinity? Right? It's not a very good approximation far away, but in the vicinity it's a good approximation. So therefore, we can pretty much use this. If we are to look at certain more approximations, so now if you look at the order 4 approximation, do you see it's getting better? The locality has increased where our polynomial is closely matching the function. We can see that now it's also probably trying to get these shapes. If we look at much more terms, so if you look at, let me just change this to make it slightly easier to understand. So if you now look at the order 11th term, you can see that it's almost got this entire shape correct, and quite far, very close to minus 2 pi also it's able to more or less get it correctly. If you want to take this much further, now you can see that the order 13th and the order 15th term are fairly accurate. Now this was around the point x not equal to 0. We could have also done the same thing at some other point. So in this case, I am showing the approximation at x not equal to pi, and you can notice that the order 1 approximation, so by order 1 I actually just meant the order, just a constant term approximation, it's just a line, and further on you can see that the approximations keep getting better and better. Around this point you will probably need to see more higher order terms in order to see the entire waveform, because this is slightly to the non-symmetrical, slightly to the right hand side. So we have a lot of area here to cover where we want our approximation to be good. Any question on this thus far? Okay. Can you quickly work out the approximation of x square plus 2? Simple function x square plus 2 around x not equal to 2. It's already a polynomial, by the way, but you can still get different order of approximation. You can get a straight line, you can get a linear approximation, constant linear approximation, and second order term. Good. So if we look at the first order approximation as I am showing on the slides, you can simply put at x not equal to 2, you will get the expression as 4x minus 2. Did everyone get that? Now let's quickly view this in code, and then we will go on to the more important derivations. So this is the function x square plus 2. At x not equal to 2, we want to see the approximation, and I have plotted the first order approximation, which is a line. Again, I wanted to specifically show the locality perspective of the approximation. This looks like a horrible approximation, right? If you look at the entire picture. But if I just restrict the range to 1.5 to 2.5, so this range is from minus 2 pi to plus 2 pi, so minus 6.88, 6.28 to plus 6.28, the approximation looks poor. But if I had to look in just the range 1.5 to 2.5, can you notice that the approximation is fairly good, right? You can't differentiate, you can't visibly differentiate between humanly differentiate between the two functions, the true function shown in blue and our order 1 approximation. So this is what we will be making use of further. Okay. So we had fx and around x naught, this is the polynomial expansion approximation that we put, f of x naught plus f dash and so on and so forth. So, we will be taking now specific x which is x naught plus delta x, right. So, we are trying to approximate this function at the value at the point x naught. We are saying that let us consider some x which is in the vicinity of x naught. And one such way to say that x is in the vicinity of x naught is to say our x value that we are considering is x naught plus some delta x, where delta x is a very small quantity. So, do not get confused between delta x and the gradients. So, this triangle symbol is just indicating we have made a very small difference between our original value x naught. We are in the vicinity of x naught, very close to x naught. If you put x equal to x naught plus delta x in this expression, you will get f of x naught plus delta x equal to f of x naught. This does not change because we are still looking for approximating around the point x naught, and x minus x naught becomes value delta x. X minus x naught, again we have put the value of delta x, right. Now, if we take, let us say that x naught was 0.0, or let us say x naught was 2 and delta x is 0.001. Right. So, x naught is 2, delta x is 0.001. What is delta x squared if delta x is 0.001? 10 to the power minus 6, it is a very, very small quantity. So, therefore, we generally say that when we do such an expansion, delta x where it is very small, then higher order terms starting from delta x squared and all, they are very small and insignificant. So, we can neglect them. So, therefore, what we are saying is that it is a very good approximation, reasonably good approximation for very small delta x, that f of x naught plus delta x can be approximated to be f of x naught plus f dash x naught by 1 factorial into delta x, because all of the terms involving delta x squared and higher terms, they will be almost close to 0. Right. Does everyone get this? If you have got this, you should now be able to derive the gradient descent update rule. There is a bit of a gap, but I think at this point you should be able to, might be able to. So, why do not you take this expression f of x naught plus delta x is approximated to be f of x naught plus f dash x naught into delta x. Start with this and try and derive the gradient descent update rule. So, why do not you just first write this down? I will then again come back to show you the slide of the gradient descent update rule, and I want you to see the similarities and see if you can derive this on your own. Okay, assuming you have written this, the following slide shows you the gradient descent update rule. The meta level joke is that I just want you to be thinking in the right direction. Okay, probably everyone didn't get it. If everyone has signed the attendance, can you hand it over to me? I will randomly call out a few people. There. Okay, how would you go about this problem? How would you link the first order Taylor series approximation around the point x naught to the gradient descent update rule? So we stopped at this point. The first order approximation of the function f of x around x naught, we are not going very far, it's just x naught plus delta x is given as the following. Now we'll first, so this is the general Taylor series expansion that we have written. We can also now write it in the vectorial form. I'm specifically writing in the vectorial form just to show you the generalized version of this. Everything else is the same, just the derivative is replaced with the gradient and certain shape issues you need to consider. Now, when we want to solve an optimization problem, we are using gradient descent. What we said is that we'll want to find out a delta x such that f of x naught plus delta x is minimized, because that's your optimization problem, right? You want to minimize a function of f, so you want to minimize f of x naught plus delta x, and it's an iterative algorithm. So what you're saying is that let me pick up a delta x. I am currently at the point x naught. Let me pick up a delta x such that f of x naught plus delta x is smaller than f of x naught. Right? My current function value is f of x naught. I want to pick up a delta x, or I want to move in a certain direction with a certain delta such that f of x naught plus delta x is smaller than that. Right. So if we progressively keep reducing the function's value, keep taking steps in which the function value reduces, we have solved the optimization problem. Right. So we wanted to choose delta x such that f of x naught plus delta x is minimized. If we look at now this expression, f of x naught plus delta x, it contains two terms, f of x naught plus this gradient of f of x naught evaluated at f of x naught and delta x. Now, if you notice f of x naught, it's a fixed value at that point, right? So x naught is given to you, f of x naught is a scalar that you'll get, it's a fixed value that you'll get. Now the only thing which you can do to minimize this quantity is to minimize this quantity, which is the gradient times this expression, right? Now think of, if you want to minimize these two quantities, you can take them to be as vectors, you want to be taking them to be opposite to each other with a phase difference of 180 degrees, right? If two things are at a phase difference of 0 degree, the dot product is maximized in the positive direction. If they are orthogonal with a 90 degree phase difference, the dot product gives you a 0. If they are 180 degrees apart, the dot product is -1. So this is what we will be saying, that delta x is some minus alpha times the gradient of f evaluated at x naught, right. So we have said that delta x is in the opposite direction of the gradient of the f evaluated at x naught. We are not talking about the magnitudes, we are just saying it's in the opposite direction. If they are in the opposite direction, two vectors are in the opposite direction, their dot product will be negative, right. If they are in any other direction, let's say 0, the dot product would be high. If they are at angles 90, the dot product would be 0, but to get the minimum dot product, you would have to choose them to be in the opposite direction, right. So therefore it would help to think of, right. So let's say you are at some point, any particular point in this space, you can look at the arrow there, right. This arrow gives you the direction of the gradient. Now if you want to increase the function, if you want to increase the function, at the maximum pace, you go in the direction of the gradient. But our goal is to minimize the function, which is you go in the opposite direction of the gradient, right. So, if you are at any point and your goal in this specific example is to come at 0, 0, you move in the direction of the negative gradient, right. And that is what we have also proved, one via intuition, second via the first order Taylor series expansion. That if we keep delta x to be minus alpha, which is some scalar, times the gradient, which is a vector, we can then minimize f of x naught plus delta x, right. So, alpha is some scalar, which is typically called the learning rate also in optimization algorithm, or the step rate in optimization algorithm. This thus gives us, so we said that we are currently at x naught, we want to move from x naught to x1 or the first iteration point by moving a small value delta x such that the function's value is reduced, minimized. So, we then take the delta x to be some minus alpha times the gradient vector evaluated at the point x naught. So, therefore, we can write x1 vector equal to x naught vector minus alpha times the gradient of f evaluated at x naught, which is the same as the gradient descent update rule which we saw. This is a slightly difficult topic. I am happy to answer questions. So, let us go over this again. So, if we just start with the vector form, is x naught a scalar or a vector? It is a vector. If we had taken this example, what would be x naught? It would be a point in the 2D space, let us say 2, 2, right. What is the gradient at any point at 2, 2? What would the gradient be? It would be some vector in this direction, in the diagonal direction, right. So, the gradient is also a vector of size 2, x naught is also a vector of size 2. So, you want to move from the point 2, 2 to some other point in the xy plane, again a 2D point, such that the function's value is minimized. The function's value at 2, 2 is 2 square plus 2 square, which is 4 plus 4, which is 8. If you moved in the direction of the gradient in some alpha step, you maybe get the value 2.5 and 2.5, right. So, which would make it 6.25 plus 6.25, but if you move in the opposite direction, let us say you get the value of new values of x to be 1.5 and 1.5. The function evaluated at 1.5 and 1.5 is 4.5, which is smaller than the function evaluated at 2, 2, right. So, we want to move in the negative direction of the gradient. Okay. So, this particular quantity is called, as I said, the alpha is called the learning rate or the step rate. What should you set its value to be? Is it a parameter or is it a hyperparameter? Hyperparameters are those set of numbers or set of parameters which you fix before you start the learning process. So, in this case it is fixed, typically set to a smallish number 0.01, 0.001, something like that. But how small or big should it be? Can we also learn a good alpha? So, this is a homework exercise for you. So, search for terms like line search and WLFE conditions. So, these two terms if you search, you will be able to find out some nice ways of finding a good alpha. Line search algorithms and WLFE, Wolfe conditions. And now we can see gradient descent in action over a simple problem. Over this problem, this function that we are trying to minimize is x square plus 2, which we have already seen. We have to start off with an initial value. Let us say initial value is 2.0. Our function's value at the initial input is 2 squared plus 2, which is 4 plus 2, 6. and we'll keep on making first order approximations, and then we'll be moving along those. Right. So in this loop, I start with a certain x naught. I just initialize the variable xi equal to x naught to indicate the value of x at the ith iteration, and I find out the gradient of the function f with respect to the input at the ith iteration xi, and I just apply the gradient descent update rule. The new value of xi is the old value of xi minus the learning rate alpha into the gradient of f at the value xi. So I initially started with the point 2. What I did was to construct a first order approximation, right? And in that I am trying to move in the x, in this case I have to move x from x naught to 2, I will be moving in the left direction using this approximation, and the next point that I will get via the gradient update rule would be x1 equal to 1.6, which you see now is the y value for x1 is lesser than the y value for x naught. So therefore, you are moving in the right direction, and the approximation you will also keep seeing at each stage. If I were to do this for another iteration 3, you can now see that I have moved from 2 to 1.6 to 1.28, and the functional value is also changed. If I do this for 10 iterations, you are seeing all these approximations. You are also seeing that the gradient or the slope of the line which you are now drawing is now gradually becoming close to 0, which means that you are coming close to the optima. In this case, it is a local optima. And you can see that you have gone from 2.0 to 0.27 in 10 iterations, and the value of function has reduced significantly. But this was with learning rate equal to 0.1. Let me just go back and do just 4 iterations. Right. So in 4 iterations, I went from 2 to 1.02. It seems that I am going in the right direction and my optimization is behaving nicely. What do you think will happen if I increase the alpha to a very large quantity? If I increase alpha to be very large quantity, in this case 0.8, I went from 2 to minus 1.2 to 0.72 to minus 0.43. So I am each time skipping over the local optima, I am jumping on the other side, but still overall I am reaching there, right, because this is still a low enough quantity. If I were to make this even larger, can you see that I have just gone out of the scope of this, right? So from 2 to minus 2.8 to 3.92 to minus 5.49. So in this case I am not converging, I am diverging. So therefore, typically we want to choose smallish learning rates, but the problem with small learning rates could be if it is a very small learning rate. I have gone from 2.00 to 1.99. So the difference has only occurred in some third, fourth decimal place. So therefore, you do not want to be choosing a very small learning rate, you do not want to be choosing a very large learning rate. From the learning perspective, it is a hyperparameter. How do you find out a good learning rate? How did you find out the good depth of the tree? K-fold cross validation, nested cross validation, some cross validation strategy. Similarly, if you want to optimize, if you want to figure out a good learning rate, you can also find that via hyperparameter optimization. So typical hyperparameters in such optimization could be your stopping criteria, your learning rate, your number of iterations, etc. Or typically the other way in which people do is they also see how difference in the gradients. If the gradients are not changing much, you stop them. There are a lot of variants to these optimization problems, including things like learning rate schedulers, where you don't use a fixed learning rate, but the learning rate is also changing. Typically, in simple algorithms, the learning rate reduces over time. In others, the learning rate can also cycle through. It can increase, decrease, increase, decrease. So typically, the learning rate schedulers, what you may want to say is that you initially have no clue about the solution. You initially have a large learning rate and then you reduce it. So you quickly move initially, make some jumps, and then you use smaller learning rates. Any questions? Yes. So now we'll discuss gradient descent in the context of linear regression. Firstly, there are three terms which students often get confused with: the loss function, the cost function, and the objective function. The objective function is the most general term you use in optimization. You want to optimize over an objective function. The other terms are the loss function. Think of loss function as the cost, the penalty which you have to pay when you get a single data point wrong, right? So typically you define the loss over a single data point. You define the cost as an aggregation of the loss function over n data points, and the objective is a very general term for defining any function which you want to optimize, right? So therefore, typically we use cost and objective functions interchangeably. So what we are saying here is that you compute the loss, let's say the mean squared error or the squared error over a single data point. Your cost function becomes the mean of the squared errors over the n data points, and that is what your objective function is. In many of the machine learning problems, we see that the cost function you can aggregate directly over the loss function. So we call such functions as decomposable functions. You can decompose the cost over the training examples, right? The overall loss that you get is loss of data point 1 plus loss of data point 2 plus so on and so forth. So RMSE, accuracy are such kinds of metrics, which RMSE is one kind of metric which will be decomposable, but there are certain kinds of metrics which don't decompose over the training examples. This is a good question for you to prepare for quiz. Figure out such functions. So we'll now do some action. We'll solve gradient descent over this problem. We have a data set of x1, y1, x2, y2, x3, y3. We want to learn the relationship. We already know by looking at the data. We have to initialize the theta vector to be 4, 0. Our step size we choose to be 0.1. We want to solve it for 2 iterations, and our y0 is this form. So way to go about this is, we know that for linear regression we can calculate a y hat like this. We know that the error that I get on individual data point is y minus y hat, right? So y is 1, y hat is theta naught plus theta 1, y is 2, y hat is theta naught plus 2 theta 1, and y is 3 and y hat is theta naught plus 3 theta 1 corresponding to this. So theta naught plus 1 into theta 1, theta naught plus 2 into theta 1, and theta naught plus 3 into theta 1. That is my predictions. I can compute the 3 individuals epsilon i's, and I can square them up, add them up. I can just simplify this expression to get a function of theta naught and theta 1. I am using mean squared error instead of the sum of squared errors. So I have this function of theta naught and theta 1, which I want to now optimize using gradient descent with the initial values that I have given us 4, 0. Can you find out the gradient of this function in 30 seconds with respect to theta naught and theta 1 in your notebooks? You have a function of theta naught, theta 1. Find out the gradient of this function. So it will be a vector containing quantities of theta naught and theta 1. Whenever we get such functions, you should think of, we pass in a vector as an input, we get a scalar as the output. We can compute the gradient. So, you can compute the gradient in a general way in the form of epsilons, in the forms of thetas directly, or the expression that I had given you. Other way to also look at this problem is what happens in the surface plot and in the contour plot. So, I started with theta naught equal to 4, theta 1 equal to 0. Now, you can notice the shape of this. This looks like some ellipsis. This is also an interesting question I won't ask in the quiz, but why is the shape of this contour an ellipse? So, our objective is to now move this point, our estimate of theta naught 4, 0 to something which is an inner ellipse, gradually reaching as close as possible to 0. In this case, you will be able to reach 0 because we know the exact function, because the data is a line. We can code this up. Right, so this is the function I have written. I have written it in terms of x and y, same as theta naught theta 1. 14 plus 3x square plus 14y square minus 12x minus 28y plus 12xy divided by 3. I start with the original tensor 4 and 0. Again, I am doing this with a function which accepts two scalars. You could work with a function which accepts a vector. And that is how you do typically in practice. We would start with the theta vector. I can compute the gradient with respect to the function f with respect to the different arguments 0 and 1, pass in the original value x naught y 1 and get my del x del y, which I get to be 4 and 6.667. I have kept alpha to be 0.1, and this is the main gradient descent update rule. I compute the gradients, I do xi equal to xi minus alpha into del x and yi equal to yi minus alpha into del y. Now, I typically, as I mentioned, I would typically do this as theta equal to theta minus alpha into the gradient with respect to theta directly. You can notice once this runs, the xi yi's go from 40 to 3.6 minus 0.67, 3.5 minus 0.55, so on and so forth, to 2.5 and minus 0.1. And in the contour and the surface, if you look over carefully, you will notice that it is slowly moving towards inner contour circles where the value is slightly smaller. Given the very small jump that we are making, it is not that easy to appreciate the jump. If we choose a slightly bigger learning rate, we may be able to see, but at the risk of overshooting. Let us hope overshooting does not happen. Okay, we are overshooting here, if you see. And so, in the contour plot also you can observe how we are overshooting. So, we are now constantly moving towards further and further contour plots. We are moving so far away that it has just broken my code because I put certain limits. But in essence, what you will see is that over iterations, you will keep updating the values of theta naught theta 1s, and in both the surface and the contour plot, you will be able to see the values. With the cost versus iteration, you would be able to see that the cost or the objective value over the iterations will rapidly decrease, and then it will more or less stabilize, which means that we have converged. And in terms of the fit, so our fit was theta naught plus theta 1 into x. Initially, the fit was poor because we had chosen theta naught equal to 4 and theta 1 equal to 0. And if we gradually look at the different iterations, we will see that our fit in terms of line also keeps getting better. We'll stop at this point. In the next class, we'll look at stochastic gradient descent and why it's very popular and very commonly used.